Hi Year 12s, and Mr. Lim here again, and this is our first video on soaps about the action of soaps. Okay, so we're going to learn how soaps work, and you should be all excited. So, the action of soaps. Soaps are substances that can dissolve in polar and non-polar substances. Okay, so that makes things like water and oil. They have a non-polar region of the molecule and a polar region of the molecule. Okay, and so we draw this generally like this, where there's a polar head and a non-polar tail. What do you think the non-polar tail is made up of? It's a really long carbon chain. Okay, CH2, CH2, so on and so forth, all the way down there, all the way there. And the polar head is, in general for soaps, it's made up of a carboxylate ion. Alright, so soaps are the sodium salt of long chain hydrocarbons with a carboxylate end group on the end. So long chain hydrocarbons, that's this part there, that's the non-polar part, with a carboxylate group on the end, right, which is that part, which is the polar head, right? And soaps, because you just can't have negative ions by themselves, are the sodium salt of them. So they will have a sodium there to make it a solid form. So when you're talking about a bar of soap, you have a sodium salt of a long chain hydrocarbon with a carboxylate group on the end, and then when you put it in water, the sodium and the soap particle separate, and then they do their thing. All right. So when placed in a polar solvents, they will orientate themselves into micelles. Let's go through what actually happens. Okay, so here's your polar head and your non-polar tail. Okay, and here's another polar head and a non-polar tail. Okay, and they're all surrounded by little water particles everywhere. Okay, so these non-polar tails don't like being in water. So what they're like is like, oh, let's go find something non-polar to hang around with. And the only thing that's non-polar are each other. So instead of that one being over there, it's going to be like, hey, let's hang out together and put our polar, non-polar tails together. And then another one will form, and then another one will form, and then another one will form. But they're not just going to form like one long line. Eventually, enough of these gather that they're going to orientate themselves into a circle. Okay, well, technically it's a sphere because it's a three-dimensional shape, but you get the idea where all of these non-polar tails go on the interior and the polar heads go on the exterior. Okay, that's my seal. Okay, and like if you have to remember that these all come from sodium salts of these things. Okay, and so they're just kind of like spread out into like some sort of ionic lattice or something like that. Okay, so the non-polar ends of the soap molecules will aggregate together, so that's the non-polar tails will come together and form a non-polar core, and then the polar ends of the soap molecule will be exposed to water to form a polar shell. So think of a ball with all of the polar heads on the outside and all of the non-polar tails on the inside. Okay, that's a mycel. Okay, so this way both polar and non-polar substances can be surrounded by substances that they can bond well with and is energetically favorable. Okay, the non-polar tails form dispersion forces with each other, so on the inside of that shell thing, right, you have lots of dispersion forces going on, and they all bond together really well. And then on the outside, the polar heads form ligands with water molecules, and so they're really happy as well. Right. So during the washing process, like if you put some soap in water or some detergent in water, mycels form in the water. Then when you shake it about, the mycels are broken up and they look to reform. Okay, so instead of it being into a nice circular spherical shape, you move the water around a bit and they break apart and they look to reform. So now all of a sudden you've got a few of those things floating around in the solution and they're not right next to each other. If any oil or grease is present, the soap particles can embed themselves into their non-polar oil particles. Okay, so if there happens to be a non-polar substance present, part of those soap particles will end up embedding themselves into the oil. Which part? The non-polar tail. Why? Because it's soaps are non-polar. Okay, so that's how the soap particles get into grease. Remember, you've got to agitate the water to break the micelles, and then they can get into the oil particles. Right. If enough soap particles are present and the grease is agitated, then the soap particles can completely lift off the grease. So what happens is that, okay, this is the grease, okay, and then you get lots of soap particles on it. Okay, if you agitate it and you shake it a bit, you can get this kind of lifting action, okay, because you pushed it with your sponge, which is there, you've pushed it that way, okay, and when you pushed it that way, you've got a lifting action, and where they were all on the outside before, now they're exposed to the lower part, and so like a few soap particles can be like, hey, look, stuff, and then they can go shove their tails in there. All right, you agitate it some more, and you know, more of it comes off. Okay, again, the polar heads on the outside, the non-polar tails on the inside. Okay, and then you agitate it enough, eventually it comes off the entire surface. Ooh, let's see if I can draw this. Comes off the entire surface and is surrounded by soap particles. Okay, since it's no longer connected to that surface, it can now float in the water. Okay, and that's how the grease lifts off. Okay, once the grease is then surrounded by the soap particles, can float in the water, and so when you pour away the water, the surface is now clear of any grease particles. Okay, which is kind of useful. A warm solution of soapy water is recommended for cleaning, as the heat from the water also increases the temperature of the oil. That makes it slightly less viscous. Okay, so viscous is like honey. So high viscosity is like honey, low viscosity is like water. So it's like kind of whether it's runny or not. So when you increase the temperature, the oil becomes more runny, and then you can get the more of the micelle or some more of the soap particles in it, and then easier for the agitation to move off the surface. All right. Agitation is also, remember, to break the micelles and to partially lift off the grease. Okay, and I think that's it.